Questions, I know. Should we start with 9 or who was 9? Can I borrow your book? Yeah, real quick. Is that will work, right? 6.1. All right. Number 9. Integral natural log 2x plus 1 dx, right? Now this problem is in the section on integration by parts, right? However, we did come up with a formula for the antiderivative of natural log of something. And I said you could write that on your formula sheet. So you should have written down on your formula sheet the antiderivative of natural log, I don't know if we used x or u, x dx is equal to x ln x minus x plus c, right? Is that what you have written? So that's a formula you should have. Now, if you want, you could replace all the x's with u's. Oh, by the way, that I was collecting that coming by and seeing if you did your homework for 6-1 is a quiz grade. That's the formula. So coming back over here, remember this? Remember we did this in class, sine ax plus b dx, and we said, look, anytime you have a trig function with a linear expression in it, it's just 1 over a. Remember that thing that we did? Okay, you can do the same thing here because we have the natural log with the linear expression in it. But I'll actually go through I'm going to do the substitution that you could do here. Basic substitution, not integration by parts. I see that I have u is 2x plus 1. The derivative of this is 2 dx. So I have 2x plus 1 there. That's my u. dx, I just need to divide by 2 on both sides, or multiply both sides by 1/2. So half of du equals dx. So if I rewrite the integral now, this integral becomes integral natural log u times half du. Here's the half out front. And that's ready for the formula now. So this would become 1/2. Now the formula. U natural log u minus u. I'll put my plus c at the very end. Any questions? I'm not done though, right? Yeah. Yes.
So that was the formula every u would be substituted for 2x.
Yes.
But the answer has the last u is just x.
For which answer? In the back of the book?
Yeah.
Okay, I'll explain it. I'll explain that in a second. So you have 1/2. This will be 2x plus 1. Natural log 2x plus 1 minus 2x plus 1. Right? And then plus a constant out here. And now you can distribute the 1/2 through, but you're saying the back of the book, does it have the 1/2 out front or no?
Yeah, it does.
Okay.
That last x when it's minus.
Okay. Okay, so let me do this. 1/2 2x plus 1. I'm just doing this to match the back of the book. I would be happy with the answer as I had it in the previous line. But to match the back of the book, imagine that I take this 1/2 right here. Oh, wrong line. Took that 1/2 and I distribute it to this one, which puts it in front right here, right? Golly. Right? That 1/2 is going to go there, and then it's going to go to the other one. To the 2x plus 1 minus 2. So if it goes to the other one over here like this, then what would you get? What's 1/2 times negative 2x? Negative x. And then what's 1/2 times negative 1? Would be negative 1/2 plus a c. Do you see that? But the book doesn't have that, right? They don't have the negative 1/2? Because the book says negative 1/2 plus a constant is still a constant. So they say, who cares about the 1/2? It's a constant. You're adding something to it that you don't even know what it is, so it's going to be some new constant that you still don't know. So they just come in here and they say, that's a big C right there. Which you can do on any integral if you have a constant by itself, is just tack it onto the C and create a new C from it. Good question. All right. That problem was a little straightforward if you use that formula that we did in class, which I encourage you to use. I think number 15 is the next one, right? And I sent an email about this because I was surprised. Well, not surprised, but I was happy to see someone from the class email me about this problem and basically saying, what the heck, man? I have no idea what to do. Well, not no idea. I shouldn't say that, but a student that tried and beat this thing to death and just couldn't get over that hump. So let's look at it. And I think this is still unresolved. Did anybody get it?
Well, the tricky part is that e to the 2x over 1 plus 2x. It's like e to the, or u to the, it looks like it's u to the n. No, I'm sorry.
Yeah, I was trying to make it into like an arc cosine, arc tangent. Yeah. That's what I tried, but it didn't work out.
You have to separate it into 2 intervals.
I'll be honest. When the email came to me, I looked at number 15 and I was like, I don't remember this problem. And I don't know if I had ever worked it before out of this book. So when I looked at it initially, I tried a couple of things, some U substitutions. Nothing got easier. Nothing was clean. Nothing was apparent right away. So then I went through what I would encourage you to do, and that's just keep trying different things for integration by parts. So let's just look at some possibilities for integration by parts. U dv. What's one thing I could try? Just pick something for you. You want the... But you could use the whole top. Let me try a couple things that aren't going to work first, okay? So if I choose the x right here as my u and everything else as my dv, then what's wrong with that? I'm not going to be able to go from dv back up to v. How are you going to integrate e to the 2x over 1? That might be tough. That's a challenge right there. So then I go, maybe that doesn't work. And I try other things. And I keep trying and trying different combinations of things until I get to this one. X e to the 2x here and 1 over 1 plus 2x squared dx here. Does everyone agree I could choose that? It doesn't look like it's going to be nice, but watch what happens. Du would be the derivative of u, which is a product rule, isn't it? So we do derivative of the first one times second plus derivative of the second times the first. So derivative of x is 1 times the second one, e to the 2x. Plus, what's the derivative of e to the 2x? E to the 2x times 2, right? Chain rule, you have to take derivative of what's up there also, right? So I'm just going to write it as 2 e to the 2x, but then times the first function, which would be what? X. And then all of that has a dx on the end of it. Yes? And then you look at that and you say, what the hell, man, this isn't even close. Like, it just seems like we're not even close to being there. But you just have to just ride this thing out and see what happens. Can we go back and integrate dv? Can we get back up to v? Well, we have to look at this integral over here. 1 plus 2x squared dx as its own problem, right? Going back up is like its own problem. On that one, ignoring everything else, just looking at that like that's a problem on a quiz. Boom, there it is. That's a basic u substitution. Okay? U is equal to 1 plus 2x. Du is equal to 2 dx. Therefore, 1/2 du is dx. If I do that, how can I rewrite this integral? 1 over u, careful, u squared, then du, right? And then pull that 1/2 out. But what is 1 over u squared? It's u to the negative 2. And what rule am I going to use here? Power rule. The antiderivative of u to the n is 1 over n plus 1, u to the n plus 1. So this should become 1/2 times 1 over negative 2 plus 1, u to the negative 2 plus 1. I'm writing too small. Negative 2 plus 1. So what's that? Negative 1/2 u to the negative 1. Yeah. And then plus c. But when we go back up here on our v, we won't put a c there. Okay? Because we know a c is going to come out at the very, very end. And isn't this the same as negative 1 over 2u? And u is... So this equals negative 1 over 2 times 1 plus 2x. That's a lot of work to have to do just to get up to v. So, like I said, I mean, it took me like 10, 15 minutes to even get to this, to try this combination of u dv. And when I got to it, I mean, I was doing all this. I was like, okay, well, I don't know where it's going to go. Let's see. And so I went back up here and I brought my v and I said, okay, v is then negative 1 over 2 times 1 plus 2x, right? And I looked at it and I was very discouraged, as you would probably be, because what does the new integral have in it? In integration by parts, the new integral will have, it'll have u times v minus the integral voodoo, right? So my new integral is going to have v du. And I look at that, initially I go, crap, that doesn't look good, right? Put those two together. That's not something I want to mess with. Until you see this. Look at my du over here. Factor out an e to the 2x. And what would be in there? 1 plus 2x dx. And when I put this with that, what happens to the 1 plus 2x? They cancel. And what am I left with? Basically an e to the 2x with some constants. And that'll be easy to integrate. So here we go. This integral up here becomes equal to ultraviolet. So I'm going to multiply u times v, right? Ultraviolet. You agree that that's ultraviolet right there? Minus integral voodoo. Now, can I pull some constants out of voodoo? How about the negative and then the 1/2? Let's do that. So it'll become plus 1/2. And then what's left is e to the 2x dx. Because again, do y'all see that cancels? This right here cancels with this. The one that's in the denominator here will cancel with this one, which will be on top of it. They go away, and everything's great. And then the antiderivative of e to the 2x is going to be 1/2 e to the 2x. So there's a little mini substitution you might have to do here. You know, u is equal to 2x, du is 2 dx, and then that's 1/2 du is dx. And then you do that little substitution. But I'm not even going to show that. That's just at this point, that's a basic substitution. So we have, as our answer here, negative x e to the 2x over 2 times 1 plus 2x plus, what? 1/2 and 1/2 is going to be 1/4 e to the 2x, and then plus my c. And what did I say about Wolfram alpha in my email about this problem? Anyone that read it? No? You didn't? Hmm? Hmm? Was it? Hold on. I was wondering why no one replied. So no one got the take-home quiz either? No, I'm kidding. I told everyone I was going to check your homework today. You didn't get that? Of course. Let's see. Oh, by the way, if you came in late while I'm doing this, I looked at homework for 6.1. So right now would be your only opportunity to just come up here and show me if you did any homework for 6.1 so you can get credit for it. Okay, write your name on a separate piece of paper. Just write your name and turn in a blank piece of paper with your name on it. Anybody else will... You can come up if you have your homework that you think you deserve credit for. It may not have gone. I thought I sent it. Sarah, can I bring up your emails? Or, you know what, let me bring someone else up. Let me see someone I have like a minimum number of emails with. Okay, I sent the thing about the progress report. Oh man, it didn't go. Huh. Oh well. Did you get it? Did you get a reply from me? Huh, it didn't go. I don't know where it is. Oops. Well, all it said was number 15 is a beast, and if you go to Wolfram Alpha can't do it either. So, like, well, Wolfram Alpha will give you the answer, but you know, if you try and have Wolfram Alpha like help you with the steps, it'll say no steps are available for this. All right. There was no other information in that email that was, but I feel bad because I did reply to you, and apparently it didn't go through. So I wasn't blowing you off or anything. Yes. Do what? E to the 2x? So this is like a separate, completely separate problem. U is 2x, du is 2 dx, and because I'm out of room, well, I guess I can squeeze it in here. 1/2 du is dx. So I can rewrite this problem replacing dx with 1/2 du and replacing 2x with u. So the integral becomes e to the u times 1/2 du. So my 1/2 comes out. And what's the antiderivative of e to the u? E to the u. Then replace your u with 2x. So back up on this problem, my 1/4 out here comes from the fact that I already had a 1/2 out here, and that integral up there produced a new 1/2, and they went together to become the 1/4. All right. Well, back up here at voodoo, VDU, we had a -1 on the numerator here. And so when we got to the integration here where it was ultraviolet minus voodoo, we pulled the -1/2 out. And that negative and minus became the plus. Yeah, and don't hesitate to ask these sorts of questions because I do them, and if you're not seeing it, then I'm intentionally leaving little things out so that you put the question in your head, can I figure that out? If not, just ask. Other questions? Do you need to look at this? Do you need the book or anything? Anyone have any more questions from there? Yes. Oh, yeah, this, okay.
Obviously, it's we bring it down to be. Isn't it 1/u times e to the u?
One, where, here?
Yeah. So it's like 1/2 times 1/u e to the u, or no?
1/2.
1/4.
This 1/4 right here?
Because obviously it's the derivative, you multiply them together, right? After you took antiderivative of e to 2x, you get 1/4.
No, I got 1/2.
Yeah, because you're already multiplying it by 1/2. You have 1/2, and then see how it says 1/2, put the 1/2 out again.
There's 1/2 up here. You're okay with that?
Yeah, yeah.
Okay. My final answer has 1/4.
I see all that, but my question is, when you're multiplying it, when you replace the u with the 2x,
Right here.
yes.
Okay.
Shouldn't it be like 1/4 x e to the 2x because u is 2x?
1/4.
There's an x in there. There's x in there. If you bring it out. I'm really bad at asking questions.
Does anyone else understand what she's asking? But it's okay. I mean, I want to try and understand what you're asking. So let's try this again. Sure. Can you just bring it here real quick? Or, yeah. I'm all hooked up right here, so I don't want to. Okay.
Like right here, that's what you're doing. That's what you did, right?
Where?
Right here, or at least what you wrote on the side, right?
Where'd the 1/u come from?
That's what I'm saying. That's not what that is then.
No. The antiderivative of e to the u is itself.
Okay, but I just said that it would just be 1/u e to the u. Because if it was 2, then you're bringing the 1/2. You kind of get what I'm saying?
Ah, now I get what you're saying.
So I thought since
It's okay.
since u is 2x,
Ah,
I thought
now I
it should be
understand
1
you.
to the 4th to the
Let me
x.
explain that to everyone. Here's the question. Okay. Are you good? Okay, we can look at that in a second. Yes, it is. Here's the question that you're saying, if we have this, if we're following what I try to show you with like sine and cosine and stuff like that, then why wouldn't this be 1/u e to the u? Kind of like when we had integral cosine of 2x plus 1 dx, I said this would be 1/2 sine 2x plus 1 plus c, right? Yes? Okay, it's because the 2 here is the coefficient of x, which is the 2 here. Up in your problem, the coefficient of u is 1. So You actually, that 1 over u shouldn't be 1 over u. It's 1 over the coefficient of u, which would be 1 over 1. So you're pulling the whole variable out instead of pulling just the number in front.
I know what you said, it's about the 2 and the x. I guess it's not fair to me to x of x.
So essentially, you can do the same thing then, if with the e.
Yes.
Do the x, you just have 1 over
1 half e to the 2x, 2x plus 1, or whatever it is.
Yeah.
Yeah, I mean, that's what we have is basically for integral sine ax plus b. I'm going to go real scrappy here. Cosine ax plus b. You know, you can do this for any trig function that you know an antiderivative of. Secant squared ax plus b, only for linear input. Integral natural log ax plus b. Integral e to the ax plus b. All of these will be just the antiderivatives with ax plus b in it, and then a 1 over a in front of it. So like this one right here would be 1 over a e to the ax plus b, plus a constant. This one would be 1 over a, and then the antiderivative natural log of that is ax plus b times natural log. So you have to plug it into the form, but you always have the 1 over a popping out.
same thing with the quadratic formula. Like you take with like 2x squared, you take 1 over 4x.
It won't work quite that. I don't think it'll apply the same way. We can look at one maybe at the end if we have some time. Do you want me to address the issue with the question, with the answer in the back of the book?
Well, I'm assuming it's the same.
Well, let's look at it because I want to. What is the answer in the back of the book?
E to the 2x over 4
Wait. Over
4 open parentheses 2x plus 1.
that's it? Plus c. And then what was our answer? Negative x e to the 2x over, what was it? What did we have? 1 plus 2x plus 1/4 e to the 2x. 2 out. That's what we had, right? So the question is, are these the same, right? Well, I could factor out an e to the 2x. Get back here. I could factor out an e to the 2x out of both, right? So if I factor out an e to the 2x, I'm left with negative x over 1 plus 2x plus 1/4, right? I can get a common denominator.
So they just algebra.
Yeah. But should I keep going? I would get a common, I'm sorry, but I get a common, so I have to multiply this side over here by this. And then over here, I'd have to multiply by 2 on top and bottom. So my new numerator is negative 2x plus 1 minus 2x over my common denominator 4, 1 plus 2x. And then on the top, this cancels. And then what was still out here? E to the 2x. Yeah, I forgot to put this one was positive. Sorry. And then we have 1. So that's e to the 2x over 4, 1 plus. Yeah, that's right. Yep. Whoa. I want you to get what I got, but I always think you should challenge yourself to try and get your answer to look like the book, because there's a lot of algebra in there. It's good practice. All right, well, anything else out of the homework? 5? What is it? Integral? T? E to the negative 3t dt. So on this one, you cannot, you can't use just the general formula for e to the negative 3t because you have a t in front. Does anybody see why the integration by parts would be good here? Yeah, if u is t, exactly. When you have integration by parts, I really have been trying to get you to see that whatever you choose for u in the new integral, it's its derivative. And if we choose t for u, then in the new integral it will be a 1, which is good because it goes away. And then in the other one, I have e to the negative 3t dt. Okay, let's see if we learned anything from what we just went through. What is the antiderivative of e to the negative 3t? Negative 1/3 e to the negative 3t. Is that right? Okay. Du is what? 1 dt. And then when I look at voodoo, I like it. Because it's just going to be, an e to the negative 3t again. I'm going to pull a constant out, but any questions? All right, so this equals ultraviolet, which is negative 1/3 t e to the negative 3t. That's ultraviolet. And then, we're going to have minus, but then on the v du, there's a negative 1/3, which I'll pull out. So it'll become plus 1/3 integral of e to negative 3t dt. And that's nice because we have to integrate e to the negative 3t again, which we just did a second ago. I'm going to come down here. This equals negative 1/3 t e to the negative 3t plus 1/3. Now, what's the antiderivative of e to the negative 3t? Negative 1/3 e to the negative 3t. Here's my plus c. So minus a ninth. That would be acceptable on the test. Would that be what's in the back of the book? Probably not. They probably take out a negative 1/3 e to the negative 3t, which leaves them with a t, right, plus 1/3 plus c. So they factor a negative 1/3 e to the negative 3t out of both terms, and then that leaves you with this. No. I like I said, I'll be completely happy with this. What I won't like is if you leave it like this. I mean, at least multiply your constants out, clean it up that much. The factoring part, Leave it like the top. Just leave it like the integral. Just leave it like the original integral. Yes. Here? You mean, are you talking about right here?
Yes.
Well, when I did the diagonal here, right, there's a negative 1/3. I pulled that out of the integral, and it's now sitting right here.
Yes.
And it becomes, okay, that's not what you're asking then?
Should it be? No. I multiplied v.
Oh, you did v or t e to the? Oh, okay, I see. Yeah. It's voodoo, not uv. It's not uv in the integral. Okay. I'm going to go back to where we finished class last time. We hadn't done this one right here. Is there anyone in here? Are any of you getting together and doing study groups at all? Is everyone just flying solo on this? No study groups?
It depends how hard to come with it. If it's a little complicated, we'll probably meet up after that.
Okay.
From your office.
I encourage you to form study groups. Really, I know it's hard to work times out with people, but try and find some people that have similar schedules to you, and even if it's you helping other people, it's good for you to show other people how to do problems because it solidifies what you know. I encourage you to do that. It's kind of a little late for our test on Thursday, but any ideas? All right, let's just let u be cosine inverse x. All right. That okay? What was that a question? Did you withdraw the question? Okay. I understood that one. I understood what you were asking. Do you know the derivative of u? What? Where'd you get that from? Oh, you aren't looking off formula sheet? Oh, good job. So where did he get that from other than his brain? Where would you get that from? Is it right? Okay. All right. Well, close. It is negative. Okay. So you go to your formula sheet. What page was that on, if you don't mind? 5. On page 5, it has derivatives of inverse trig functions. So there's your derivative. Jeez. Does anybody remember where that derivative came from? Like in your Cal 1, did your instructor show you why that derivative is what it is? Yeah. Okay. Triangle. All right. Well, I'm just going to take it that you were either shown it or just shown the formula, and there it is. If you want to know why the derivative of that is that, feel free to come by my office. I'll be happy to show you. What does our dv have to be then? If we chose that to be that, dx? And that'll be an easy antiderivative. Antiderivative of dx is x. Now let me take a quick look at what voodoo is going to be. It's going to be x times this, which means I'll have an x on top, right? All right, let's see what happens. So this becomes ultraviolet x arc cosine or inverse cosine of x minus integral voodoo. Is it going to be minus? Plus. Because again, every time I'm doing voodoo, I'm looking at signs. I have a negative on my du. So since the integral is being subtracted, I'm always, I'm changing that sign to a plus, and I'm doing it right now. But because I might be confusing some people, I'm actually going to show what I'm actually doing. V du. There is exactly, without me doing any simplification, that is ultra. Well, I have my ultraviolet backwards. This is my violet ultra minus V du. Now do you see where the negative is going to come out and become the plus? Outside? Yeah. So this equals x cosine inverse x plus integral x over square root 1 minus x squared dx. Any ideas there? We did? Something like it? How? How did we do it? Let's do this. Hit the reset button on your brain right now and go back to the very first type of thing that we did when we looked at integrals. Substitution. Do you see something in its derivative? I see 1 minus x squared, and I see its derivative, which is really negative 2x, but we have an x, so we're off by a number. So this would be a basic substitution. Let's let u be equal to 1 minus x squared. Du would be negative 2x dx. I have an x dx up there, right? I have an x dx up there. I have my 1 minus x squared here. So we're off by how much then? We have to divide both sides by negative 2. So negative 1/2 du equals our x dx. So what does this integral become? And remember, I'm just doing this integral right here. Just this. That's all I'm focusing on right now. What does that integral become? Negative 1/2 integral 1 over square root of u du. Isn't it? And that's a power. Yep, u to the negative 1/2 du. So I'm rewriting 1 over the square root of u as u to the negative 1/2. And now I use, integral of u to the n is 1 over n plus 1, u to the n plus 1. Or you just remember what I told you about the derivative of the square root of u is 1 over 2 root u, where we don't have the 2, so we'll be off by that. But either way, she'll be able to get this. Well, or maybe this is what you were saying. If you actually take this 2 right here, or I should say here, and just put it right back in there next to the square root of u, then that is the exact derivative of square root of u. No matter what, though, at the end, you should come out with what here? Negative 1/2 times 2 root u, which is the same as negative root u, but u is 1 minus x squared. Now that's just that red part, that red integral, right? Up there? So I think I'm ready for my final answer. The antiderivative of cosine inverse x dx equals x cosine inverse x minus square root 1 minus x squared plus c. As you might expect, you can do this for arcsine and arctangent also. Any of the inverse trig functions, you can work it out a similar way. That means on a test, I might throw the sine inverse out there. I might not. Or I could do cosine inverse.
Does it mean the same thing when they write it out? Arc sine
Yes. Oh, okay. Yeah. There's different notations. Arc sine of x is equivalent to this. These are the same. The advantage to writing arc sine is that if you're using word processor, typewriter, it's easier to type arc sine than it is to do a superscript with a -1, and so it just makes things flow faster. This is just notation, everyone. 11:51. What time do we get out here? 12:40? Seems like it's just creeping by today. All right, let's talk about reduction formulas. So if you look at, the formulas that I've given you, can I see them real quick? Are these all of them, the ones you're allowed to have on the test? When it comes to the integrals, which is, oh, here they are. Yeah, when it comes to your integrals, I only put like 20 something on here. Right? 21. These formulas, all of the formulas here have been proven somehow, okay? If you go into the back of your book, there's more formulas. There's like 100-something formulas in your book. And a lot of them are of this form, where they give you a general formula that you can apply to any problem that looks like this. So let me just show you how the formula works, and then we're going to prove the formula. So how does this formula work? Let's say, for example, I'm given integral x to the third e to the x dx. The reduction formula says, look, instead of going through all your integration by parts and doing it right, the answer to this will be x to the n, which would for us be what? X cubed, right? Because what's our n in this problem? 3, that's our n. Everything else in the problem is the same as the formula. So x cubed, then what? E to the x minus n, what's n for us? 3, integral x to the n minus 1, 3 minus 1 is 2, e to the x dx. See how that formula worked? But you're not done, because now what you can do is you can apply the formula again to this, because doesn't that look like integral x to the n e to the x dx? So now we have a new n. So this would become equal to, we still have the x cubed e to the x minus 3, but that new integral now is what? X squared e to the x minus 2 integral x e to the x dx. But you can go one more time on just this. And what's happening every time I do the formula? It's reducing that power of x, right? That's kind of why they call it a reduction formula. It's a formula that keeps on allowing you to reduce your problem into simpler and simpler integrals until you're done. Follow that? Okay, so let's do it. We're going to take this the whole way. So this would become x cubed e to the x minus 3 bracket. I'll multiply it all out at the end. Minus 2, another bracket. What does the integral x e to the x become? X e to the x minus, what's n for us here? 1. So 1 integral x to the 0, right? Which would be 1. So all that's left here is what? E to the x And we're happy about that because what's the antiderivative of e to the x? E to the x. So we have x cubed e to the x minus 3 x squared e to the x minus 2 x e to the x minus e to the x close, close. So you distribute your negative 2 through. After that, you distribute your negative 3 through, and that would be your final answer. X to the third is where we started. Should I give you that problem on the test, but make it x to the 30th? No, I shouldn't do that. Well, what I'm going to do is I'm going to give you on the test something for you to show. And then after that, ask you to use it in an example. So like what I just did right now is I gave you the formula, right? To start the problem. And then we used it as an example for this, right? What we have not done is what this problem was supposed to be. Show that formula is true. That's what we have to do. This is just showing how the formula works. But now let's get to the heart of the problem. Show the formula is right. So to answer your question, you're going to be given the formula, but you're going to have to prove the formula is true. It's not as bad as it may look, okay? It may look like, how in the hell are we going to get to this, okay? It's not that bad. Here we go. So I'm doing the work on that. I'm going to show that that reduction formula is true. Here's the original integral, right? That's it. I want to show that that turns into the reduction formula. So let's use integration by parts. What would be a wise choice for you? X to the n. Why would x to the n be a wise choice? Because every time we do integration by parts one time, the power on x to the n comes down 1, doesn't it? And eventually will go away. That forces my dv to be what? E to the x dx. So let's go back up. Let's get v. What's v? E to the x. What's du? What's the derivative of x to the n? N x to the n minus 1 dx, right? All right, what's ultraviolet minus voodoo? Ultraviolet is x to the n e to the x minus, now look at your voodoo here. Which of these numbers here is a constant? N. So that n right there, can it come out of the integral? So the n comes out, and what's left in the integral still? X to the n minus 1 e to the x dx. And that is the reduction formula, isn't it? So it's not as crazy as it may look initially. Agreed? That's what we like to do in math, is we like to come up with generalizations if we can, but it has to be very general. I mean, this will handle any time you have a power, x to a power and e to the x next to it. This will handle it. Now, I want to do one more of these, but I need the book. Let's try another one. I'll just grab it. Thank you, thank you. I don't know why I keep leaving my book in the office. Let's do one that's more challenging. That one was pretty straightforward. Here we go. Man, that one's tough. That one is tough. Yes. Well, it's understood that n is not a function. Yeah. In the formula, I mean, n is understood to be integer Or it could be, yeah, but normally integer is the way. If they don't say it, that's what they imply. Let me see here. Let's try something first. Before I get to this, let's try something. Let's see if we can do this one. What's the antiderivative of secant cubed x? Nope, no formulas. Just break it up. Secant and secant squared. Okay, so this is probably going to get us there, but what made you do that? Okay, so you realize that if one of those was a secant squared, you know the antiderivative of secant squared is what? Tangent. That has to be kind of there for you to have that intuition to split it like that. So the secant squared is going to be what I want to take the antiderivative of. So my dv is going to be the secant squared dx, x dx. And that forces my u to be secant x. So what would v be here? Tangent x. And then what would du be? What's the derivative of secant? Secant x, tangent x, or tangent x, secant x. Right? Derivative secant x, tangent x. Agreed? Oh, so this will become ultraviolet minus integral voodoo. What's voodoo? Secant x tangent squared x dx. Oh shit! What now? Excuse my language. I just have a. Sometimes I cuss. I'm sorry. So what are we going to do with this? It's not obvious here. Okay, if we do integration by parts, what would be your u and what would be your dv? You want to do tangent? You could go cosine and sines here. One over cosine. The other one would be sine over cosine, but squared. Yeah, I mean, there's a lot of different options. See, the problem that I'm seeing with the VDU, or the problem you should be seeing with this, is that you can't really pick your dv to be tangent squared x dx because you don't know what the antiderivative of tangent squared is. Okay, so could you let it be, so split that secant and tangent back up and make it a secant x tangent x, put that here, which would force your other one to be what? A tangent x. Then what would you get? You would get secant squared here, and back you would get secant, and you multiply, and you would get secant cubed again. You could. What will happen, though, is in the previous problem where we did that, when we did the subtraction. One of them was the integral and the other one was like 1/4 the integral. And so when we subtracted, it came out to be, like 5/4 or whatever it was. So the integrals was still there. Here, if you do it, when you subtract on both sides, they'll go away. It'll be gone. They'll cancel. But I wanted you to see it because that you could try that, but it's gonna you'll at the end be like, what the hell?
The integral, it would be minus the integral of secant cubed and add it to both sides to get 2 integrals secant cubed.
But this integral here is going to become ultraviolet minus voodoo, and we have a minus here, and that'll become a plus, and then we do wind up subtracting it. Let secant x be what? Oh, yeah, the reduction formula. Can't use that unless it's x. Your variable has to be x to a power. It can't be a function of x. Substitution, what would your substitution be? Secant squared x. Are you saying convert tangent squared into secant squared x minus 1? Is that what I'm hearing? Could you? Yes, absolutely. You could rewrite this as secant x times secant squared x minus 1 dx. That's what you were saying, right? Whoever's saying that, yes? I hear voice. That's you. Okay, all right. You could do that. Then what would happen? Minus what? Secant cubed x minus, how about I go, oh, yeah, I'll put it here. Minus secant x dx. Is that right? You could split that up into 2 integrals. So we didn't talk about this. How did we get from here to here? It's Pythagorean identity. The Pythagorean identity, sine squared plus cosine squared equals 1. The other one is tangent squared x plus 1 equals secant squared x. And then there's some with cotangent squared, and so there's 3 of them. This one converts tangent squared into secant squared minus 1. So my new integral becomes, let's see, or this integral, I can split that into 2 integrals, can't I? Now, what is this all equal to? What's the left side of this integral? Or this left side of this? Integral secant cubed x dx. Do you see here we have the same integral appearing on both sides? So we can add it to both sides, can't we? Add it over here, and how many would we get on this side? 2 of them, wouldn't we? I'm gonna take, since I see the integral I want is actually on the other side also. So if I add the integral on this side and add it over here. See, I'm adding, not subtracting. If I were subtracting, they would go away, but I'm adding. So if I have an apple and an apple, I get 2 apples, right? So this is going to become 2 integrals. Ooh. Equals secant x tangent x plus, the only thing left over here is integral secant x dx. And don't you have a formula on your formula sheet for secant x? Natural log of, yep. So,
Can you go over the previous step that we added?
why I added, or
So,
going from the tangent squared to the secant squared minus 1. That okay? The yellow,
yes.
okay? Distributing the secant through the parentheses gives us secant cubed x minus secant x. That okay?
That's fine.
Okay. Next step, split it into two integrals. Distributing them.
That's where it's tricky, why are you adding?
Okay, this one went here, which makes it a negative. This one already had a negative, which makes it a plus. And now it works because you add secant cubed to both sides and it doesn't cancel. It creates two of them, which is what you want there to be more than, you don't want them to cancel out. Okay, so 2 integral secant cubed x dx equals secant x tangent x plus, what was the antiderivative of secant? It was natural log secant x plus tangent x. Is that, I'm going off. Is, then divide everything by 2. Integral secant cubed x dx equals, I'll just multiply both sides by 1/2. Why do what? Instead of doing like division by 2? Good question. It's because in calculus, so many times we're using power rule that we like to have constants out in front, right? So like if you ever have to bring a power down, you just multiply them. When you have division across the whole thing, yeah, I mean, it's just kind of like we don't, you can write x over 2 like that, or you can write it like this. They mean the same thing. In calculus, it's better to write as 1/2 x, because if that was to the 7th power, then the derivative, 7 halves comes out, or 7 times 1/2 x to the 6th. See, it just works cleaner, especially later on when we do series, same thing.
Okay.
Yes.
Back up when you were at the tan squared,
Yes.
could you pull that apart so it's secant tangents, or two tangents, and then use the integral of secant x tan x, which is secant x plus 2, and then do the integral of tangent plus
Okay. You're saying here, could you do integral, let's see, split it up, secant x, tangent x, and then have the tangent x next to it, right? Dx. Oh. Yes? Yeah? Okay. You could do that, but I think what you want to do now is you're saying, I know what the antiderivative of that is, and I know the antiderivative of that. Correct. If there was a plus between them, you'd be in business. But the multiplication is what gets you. Yep. It's for the same reason when we have something like x e to the x dx. I know what the antiderivative of each of those is individually, but you can't. Yep. It's because you're trying to reverse the product rule. And we know the product rule isn't just derivative of each one done. It's this plus, minus, or no. Derivative of this plus this times, you know what I'm saying. You know what I'm saying. It's not as simple. I mean, calculus would be a lot easier if when they taught you product rule in Cal 1, it was just take derivative of each one, multiply. All right, so let me, I don't want to embarrass anyone, but can I ask you your name? Catherine? So what made you see the tangent squared x is secant squared x? I mean, what made you think to do that? So you were just, would it be safe to say you were just kind of taking a shot at something there and seeing, I mean, like, you didn't foresee all of this happening, right? Like, you didn't see that we were going to get a secant cube and then we'd be able to move to the other side and then divide by 2? So it just seemed like maybe something would come from this. I mean, I'm trying to give you credit but I'm trying to help other people understand like where it is that came from. Exactly. You just kind of have to try though. I mean, you have to, okay, there's a formula that, Yes.
Related like to the identities, like one of the first rules of solving Riemann identities that make it the same thing. So because you have secant there, example.
Well, the next section in the book is called 6.2, Trigonometric Integrals and Substitutions. Everything we do in 6.2 after the test is going to be what do we do when we are faced with integrals that have trig functions in them, like secant cubed, or what if you have a cosine to the fourth? And we'll spend a lot of time on those. So we will have some rules of thumb, how to attack those. But this is the first time you've seen it, and I wanted you to see that we had to do an old Pythagorean identity from pre-cal. And then Sarah, also you had suggested that one integration by parts. I'm glad you suggested that because that's probably what you would probably do before the trig. You might try that, but then I would encourage you and everyone else try it, and you'll see they'll cancel, and then you're done. You can't move on after that. So this is good. All right, this is good work. Now, we don't have a whole lot of time left. That was just to build up to this problem right here. Whose book is it? Here. This is the same thing that we did earlier on the one I did with what was it that we did? The x to the n, e to the x. We showed the reduction formula. We came up with it on our own. Same thing here. Show that this is true. Now, I'm offering this to you as a bonus problem. But in light of me walking around and saying, how many of you have done your integration by parts homework? This should not be on even on the stove if you haven't done your integration by parts homework. This should be, just put it away. Integration by parts section, do all that homework first. Don't even touch this. Don't think that doing this one bonus problem is going to, cure everything. Go do all that. If you have time, you've looked at everything, you feel ready for the test, go and try this problem. Try and show that reduction formula is true. Okay? I'll give you some hints. The fact that we have that new integral has a secant n minus 2. Over there on the right side, the new integral has that. Means that you can almost reverse engineer your integration by parts table. I don't know if that makes sense. You know that integral over there is voodoo, don't you? And you know that this over here is ultraviolet. So maybe you can actually come up with this right here, what you choose for U and dV, by just looking at this. Maybe. We'll see. That's bonus. To be turned in beginning of class, Thursday before the test. The fewer people that have it, the more it's worth. So I don't encourage you to share it with everyone after you figure it out if you figure it out. Because if everyone turns it in correctly, that pretty much tells me that either it wasn't hard enough or everyone shared the answers with each other. So if you get it, be proud of it. Don't show it to anyone, and you turn it in.
It's not going to be the same thing for reduction formula.
This is a reduction formula. This is the formula that you would use if you had secant to the n, right? Like, let me apply the formula one time. What did we just do? Secant what? Cubed? X dx? If we had this formula instead, then we could have not, didn't have to do all that magic with the tangent squared being converted to secant squared and all that. We could just use this formula, which would have been tangent x, secant, what's n for us here? 3. So 3 minus 2 is 1, so it would just be secant x over 2, which is really a 1/2 in front, plus, let's see, 5 over 2 integral secant dx. But what's the antiderivative of secant? ln, all that stuff? Yes? Agreed? What was our answer? Hold on, let me go back to it here. I don't remember the 5 in our answer. Did we have it? It must have to do with that constant because we get the natural log. Well, maybe I wrote it down wrong. Let me see. Is it n minus 2? Yeah, that would be a lot better. Hold on, I may have, shoot. I'm glad if we catch this now, it's good because you'd be pissed off at home. Send you home with a problem, and I wrote it down wrong. Yeah, the n minus 2 should save us here. By the way, this is number 58 in the book. So I'm not like throwing some crazy problem. It's number 38. It's number 38 in the book. Yeah, it's n minus 2. Right here, I'll make it n minus 2. Right there, switch that. Okay, so that makes that a 1 now, right? And then that gives us what we had. Number 38. You have to show that that formula is true, which means you'll have an integration by parts table and everything else. 6.1. Make sure I covered everything I wanted to cover. Yeah. Okay, I'll open the floor up to any questions right now. Any other things out of the book? Anything out of the substitution section?
Did you answer whether we can write down the reduction formulas on our formula sheets?
You cannot write down the reduction formulas on the sheets. Because in the test, what I will do is I will provide you the reduction formula. And I will say, show it's true. If I even ask that question, but you would have it. I would never on the test say, use the reduction formula to do like secant to the 7th without giving you the reduction formula. So I would provide it for you. All right? What is going to be on the test? Maybe we should talk about that. Yeah. So just off the top of my head here, method of exhaustion. That had to do with the Riemann sums, right? I can never remember if it's Riemann or I think it's R-I-E. I can't stand the English language. You know what I'm saying. Just anything where I have to remember IE or anything like that. Method of exhaustion, Riemann sums. So what I mean by that is you need to go back and take a look at the beginning of the semester where we talked about, your first quiz. I gave you a circle, said come up with a formula for, this. I want you to understand the idea behind areas of things, right? Go back and think about, okay, we were taking a finite number of whatever's triangles or rectangles, and then we were adding them up and letting the number of them go to infinity. Just kind of revisit that whole concept. There may be vocabulary, like there might be like complete this sentence, fill in the missing word, that sort of thing. Let's see, so method exhaustion, Riemann sums. We had, you remember when we did something like find area under a function on some interval, let's say 0, 1, using limit definition? That means to find that area, you would have to do the limit as n goes to infinity of the sum k equals 1 to n f of a plus, is this starting to look familiar? K times b minus a over n times b minus a over n. That was that big formula I gave you. Remember that? I might ask you to set up the limit. I might ask you, I don't think I'll ask you to compute it, because remember there was a take-home quiz. It was like an entire page of like evaluating it. But it would be fair for me to say, give me the formula, the limit formula for this area. So you just have to fill everything in, like what's A, what's B, what's N, what's, you know. And then I could say something like, use the fundamental theorem of calculus to find the true area for a problem like that. So what would you do to do that? Integrate, right? Antiderivative of x squared is 1/3 x cubed. Then you plug in the two endpoints, subtract. So this would just be showing me, the first one would just be showing me that you remember that what it was a bunch of rectangles that we were going to add up forever. But we got this, which helped us do it a lot faster. But I want to still see that you can create that formula. Any questions on this so far? That's right. Yeah. Yeah. And be able to just plug in the parts. And remember, one of the hardest parts of it is when you do this part right here. When you plug the a plus k, b minus a over n, when you plug that into the function, it depends on what the function is. So, but I won't ask you to go any further than that. Fourth thing that comes to mind here, of course, techniques of integration, substitution, and integration by parts. If I were to break up the test into like a weight, I would say that the ideas up here are probably only going to comprise maybe 10% of the total grade. Sorry, that extends down right there. Yeah, 10 to 15, let's say. But 85% of the test, 85 to 90, will be you integrating. And then there might be some bonus in there. Bonus can be anything. It's very difficult to make a test for Cal 2, for Cal 3, because as you've seen, you can sit with an integral for a while. What I've done in the past, and I'm just going to run this idea by you, I've done before where I give you a problem where it has, let's say, the idea of substitution, right? Go with me? Let's say it's number 4 on the test, substitution. And it has problem A, B, and C. Problem C is easy. Problem B is middle of the road, and problem A is difficult. And so what you do is, for that problem, you choose which one to do. But if you go through the test and you do all the C problems, you're going to earn a C on the test. If you do all the B problems, you'll earn a B on the test. And if you do all the A problems, you earn the A. So getting it right, you can still get it right. You can still show me that you understand the basic ideas and still pass the test. Or you can go for the hard ones. Now, here's the challenge in the difficulty in the past when I've done this, is that students will go for the A, and then it becomes an issue of time because they can't get the A problems. And then they're like, I'll try the B, and then they get stuck, and they wind up doing the C, and then it's just they start freaking out because they run out of time. So would you all prefer to see something structured like that? I mean, the first couple of problems with the sums and exhaustion and all that, that's going to be everyone's doing the same thing. But when we get to the integrals, would you like to have options? Or would you like for it to just be everyone does this problem, this problem, this problem, this problem? What do y'all think? So everyone has the same exact, no options, just do these problems? Y'all feel better with that? Let's. My opinion is that the people who passed were going to pass, and the people who didn't pass were the people who weren't going to pass. It's much easier for me to grade a test. I know that's not what you're asking, but I prefer just everyone does the same problem. You know, that's what I prefer. But
she did. There were like A-level questions, B-level questions, but it was all everybody did the same one. So there's just different levels of difficulty.
well, everyone would do the same. The A-level problem would be the same for everyone.
Yeah, no.
Oh.
What I'm saying is like there's 20 questions,
Uh-huh.
and like 5 of them were C, 5 of them were B, and 5 of them were A, and then 5 were like the first 3 parts of that. So it's like if you got all the A's, then if you did all of them, you got all the A's, you're gonna get an A.
Mhm.
Some of them you got all the B's, you're gonna get a B, etc.
But you had to choose A, B, or C? Oh, so you could do some B's, some. Well, that's what I'm saying here. You could do for each problem. There might be number 4, 5, 6, 7, 8, 9, 10. For those problems, each one you can choose A, B, C. So the concepts would be the same.
How many substitution and integration by parts problems?
I'm more inclined to give you integration by parts than I am substitution. Because to do integration by parts, you're going to have to show me you can do substitution. So
So how many questions do you think are going to be for?
I can see maybe 3 problems out of the first, maybe 2 or 3. Maybe the first problem is kind of a vocabulary type thing. Second problem is just what it says there. Third problem is area, right? And then after that, you're looking at least 7 more. Yeah.
On your test, do you find people frequently are having problems with time?
It always depends on the students. I mean, people will run out of.
A students,
They'll finish with time.
running the
With throw the bonus out. I think the A students will finish with time to spare. But if someone gets stuck on an integral, we've seen, if you get stuck on an integral, and like the integral, like number 15 that we did today, I mean, that is a tough problem. I mean, that would be an A-level problem. So, yeah. Let's do this. For this first test, let's just keep it, we're all doing the same thing, okay? And we'll see how it goes. And
What happened if you got A problem, you got it wrong, and you didn't do the B or C?
that's right. It would be wrong. Yeah. I mean, it would be the same as if you didn't do a C problem. It would just be.
I mean, the points aren't any different. It's just the same.
Well, the A problems would add up to be like, think of it if there were 10 problems. If you did each A problem, they each were 10 points. So you could get 100. If you did all the B problems, they're all worth 9 points. So you could get a 90, right? Something like that.
So it's just the weight of the problem.
The weight of the problems.
Because
That's right. It'd be
if you
heavier.
get wrong, then you get an 81. If you get an A wrong, you get an 80.
Yeah. If you got all the B ones right, you would get a B. The most you could be would be. But I think just to keep it simple, let's just, everyone come in. What can you do to prepare? Do your homework. Yeah, I've done it before just to see what would happen. So,
Well, I think that's what my calculus teacher did, but she didn't really explain it to us.
yeah.
So when she let us choose an answer or choose a question, I was like, oh, this is easy. And I got a C on the test. So I'm like, what am I going to see?
Oh, so you just thought ABC, pick one. Not, yeah, that kind of sucks. All right, well, I don't think I have anything else for you. We'll see you in 48 hours, or less than that, 46.
So how does